Hello there, young students of chemistry. This is a short lecture presentation on using significant digits when we're making calculations. You should take from your binder the note sheet that has the significant digits in measurement title. It also has a diagram of the continental United States on the front of it, if that helps you find it. And you'll also need a calculator for a later segment. So oftentimes in science, we learned the other day, we make measurements. And measurements are great, and we want to report those to the correct number of decimal places to indicate the value or the precision of our tool. However, sometimes we take those measurements and we do a calculation with them in order to get a different measurement. For example, if you have a cube and you want to know the volume of that cube, you can take the measurements, length, width, and height, and apply the mathematical operation of multiplication. Density is a huge derived quantity. That's what we call it if we apply a mathematical application to it, where we would take the measurement of mass and divide that by the measurement of volume. So before we start doing calculations with measurements, it's important for us to be able to look at a measurement and determine how many significant digits are in that measurement. Now, here's the thing. It's all about the zeros. The integers or the non-zero numbers, they are all significant. It doesn't matter what the number is, it is a significant value. And there are rules for significant digits, and you may have read that in your textbook. And those rules are zeros that are captive, meaning they're in between two non-zero digits. Those zeros are always significant. The other rule is that leading zeros are never significant. So zeros that appear before a non-zero digit are not significant. The issue here are the trailing zeros. The zeros that appear after non-zero digits, we need to determine whether they're significant or not. And that is determined by decimal placement. If there's a decimal, they're significant. If there's no decimal place, they are insignificant. So those rules work really well. If you're not a rules person, I've developed this system called the Pacific Atlantic method. And Pacific Atlantic is just a way to remember present, absent. And what I'm talking about being present or absent there is the decimal place. So if the decimal place is present, we will approach the number from the Pacific. In the continental United States, if we're looking at a map of that, the Pacific Ocean is on the left-hand side of the United States. So we're going to approach that number from the left. We are going to start counting digits when we reach our first non-zero digit. That and everything following to the right of it will be significant, whether it's a zero or not. If a decimal is absent, we will approach the number from the Atlantic, meaning the right-hand side of the number. And again, we start counting at the first non-zero digit. And then we're going to continue to proceed going from right to left. And all of those numbers after the first non-zero digit are significant. So we'll use the Pacific Atlantic rule here. And we will also talk about the rules for significant digits as we do that. So here you can see I have a picture of the continental United States. Pacific Ocean over here. This is just a way to help you remember. Atlantic Ocean over here. If we take our first measurement, 40.7, the decimal place in this number is present. So we're going to approach the number in this direction, from the left to the right. Start counting when you reach the first non-zero digit, which in this case is the 4. So we have the 4 is significant, the captive 0 is significant, and the 7 is significant. So this measurement of volume has 3 significant digits. If we look at example B, 97.00 kilograms. That's a measurement of mass. The decimal is present. So we're going to approach this number again from the left and follow through counting significant digits. So the 9 is significant, the 7 is significant, and those two trailing zeros after the decimal are significant. So this value has 4 significant digits. Example C, 3,206, nope, 32,006. I'm guessing that's supposed to be a meter, a lowercase m. The decimal is absent, so we're going to approach that number from the right-hand side, and we're going to go from right to left in counting our significant digits. The first non-zero digit is the 6, so that and everything to the left of it is significant. So the 6, the 2 captive zeros, the 2 and the 3 are all significant. So this number has 1, 2, 3, 4, 5 significant digits. We have the next example, letter D there, 1,200.00 centimeters. Oops, centimeters cubed, that's a unit of volume. The decimal is present. So we're going to approach this number from the Pacific, and we're going to start counting with the 1, and we're going to continue counting. So this number has 6 significant digits, the 1, the 2, and then all of those trailing zeros, all 4 of them are significant because there is a decimal place present. So this has 6 significant figures. Take that same measurement of volume, 1,200 centimeters cubed. Here the decimal is absent, so we're going to go from right to left instead of left to right. And we start counting at the first non-zero digit, which is the 2. And then count everything to the left of the 2. So in this example, this same measurement of volume, the same quantity, only has 2 significant digits. So the difference in these two quantities is not the value of the quantity, the numerical value, still about 1,200 centimeters cubed in volume. The difference here is the tools that were used. We can see that the tools for the first value of volume were measuring length, width, and height with a ruler that had a mark for every 1/10 of a centimeter. And that would be, the last zero is the estimated digit. However, with the tool making the measurement of 12,000 centimeters cubed with, or 1,200 centimeters cubed with no decimal, that has a mark for every 100 centimeters cubed. Or I'm sorry, every 1,000 centimeters, which means that this 2 is an estimated digit. So that's why it's important to be able to look at a measurement, recognize the significant digits, because then when we make calculations with them, we need to report our number or our calculation to our tool that is the least accurate measuring tool. So we can see in letter F, I'm going to stop using the continental United States here and just go, okay, the decimal's present, so I'm going to approach it left to right. I start counting with the 5, so the 5 and the 7 and the 2 are significant, so that is 3 significant digits, and meters squared is a unit of area. And the rule is leading zeros are insignificant. Letter G, the decimal is absent, so we're going to approach it from the right and start counting at the 4, so right to left here. The 4 and the 3 are significant, so that has 2 significant digits in that measurement of mass. The trailing zeros are insignificant. That's the rule. If we look at letter H, and this is the one I always have such trouble with, the decimal's present, so we're going to come from the left to the right, and we start counting with the 2. This has 1 significant digit. But we can see that this electronic balance measuring the mass is very, very accurate. This is an expensive tool, but it only has 1 significant digit. So remember the other day when we talked about how if things are good at measuring small masses, they're probably not very good at measuring large masses. And things that are good at measuring large masses, like the scale that's weighing the trucks on the highway, they're not good at measuring small masses. So that's why this number only has 1 significant digit, even though the precision of the tool, or the accuracy of the tool, is really, really good. Okay, the last example here. 4,000 milliliters. That's a unit of liquid volume, probably. We can see that the decimal is present. So this time we're approaching from the Pacific, the left, and we're going to go from left to right, counting the 4, and then all of those trailing zeros. So this has 1, 2, 3, 4 significant digits. What I'd like you to do right now is to take a minute, pause the video, and I would like you to count the significant digits under the You Try It menu, or under the You Try It in your notes, and then turn the video back on and check your work. Okay, check your answers, please. A letter A, we have 2 captive zeros which are significant and a trailing zero with no decimal place, so it is insignificant. Letter B, we only have leading zeros which are always insignificant. Letter C, we have a captive zero and we have 2 trailing zeros with a decimal place, so those zeros are significant. Letter D, we have trailing zeros without a decimal place, so those zeros are insignificant. Letter E, same rule. Trailing zero, no decimal place, insignificant. Letter F, 2 trailing zeros, but there's a decimal place, so those zeros are significant. Letter G, trailing zeros with no decimal place, the zeros are insignificant. Letter H, captive zeros are always significant. Letter I, we have a leading zero, or actually 2 leading zeros, which are insignificant. And then we have 2 trailing zeros with a decimal place, so those are significant. Letter J, no, well, that leading zero, probably just making the decimal place stand out a little bit better. Letter K, leading zeros, insignificant. So there's 2 significant digits there. And then letter L, those are just non-zero digits, and we know that non-zero digits are always significant. So hopefully you've got a good handle on that. The issue that students have when they get a number in their calculator often is, gosh, I need to round this number. We're going to follow rules for rounding. If the number directly to the right of the place that we need to keep for significant digits is a 5 or greater, we're going to round that value up. If it's less, we're going to round it down. So here's the thing that happens. Students look at a quantity like 50,600 milliliters, and to one significant digit, they turn it into 5. Well, would you rather have $50,600 or would you rather have 5? You can't just ignore the magnitude of the number. The magnitude of the number needs to stay, and then you need to limit the number to the significant digits allowed by your tool. So if we're going to round 50,600 to one significant digit, we're going to keep that 5. That will be significant. And then after that, everything becomes a 0. So we just make that 50,000 because we know that we can make zeros either significant or insignificant by adding or removing a decimal place. And without a decimal place, they are insignificant. Now, if we plunk a decimal place on there, plunk a decimal on there, now they're significant. And we have now just created a number that has 5 significant digits instead of what we want, which is 1 significant digit. So I'm going to erase that. I would hate to lie to you. And we'll round that number to 50,000 milliliters. To 2 significant digits, now we need to keep the 5 and the number directly to the right of the 5, which is the 0. So we keep the 5. Now that 0, to the right of the 0, it has a number 6, which is greater than 5. So we're going to round that 0 up to a 1. And this becomes 51,000 milliliters. Without a decimal place, the trailing zeros are insignificant. So leave that decimal place off. So now with 3 significant digits, we want to keep the 5, the 0, and the 6. And now to express the magnitude, we'll add some zeros. So now we have a captive 0 between the 5 and the 6, which is significant, and we have 2 trailing zeros, which are insignificant. Same thing with 4 significant digits. Keep the magnitude by keeping the 5, 0, 6, 0. Now this one gets a little tricky because we have 5, 0, 6, 0, 0. Well, without a decimal place, those trailing zeros are insignificant and the captive 0 is significant. So that would have 3 significant digits. But we need to have 4 significant digits in this measurement. So let's plunk a decimal place on there, or plunk a decimal on there. If we do that, now our trailing zeros are significant, and we have a captive 0, which is significant, and 2 trailing zeros, which are significant as well. So we have 3 significant zeros and 2 non-zero digits, so that's 5 significant digits, and this creates a problem. Ladies and gentlemen, this is where your, I think, 4th grade mathematics come into play, and we use scientific notation. The only way to express this measurement to the proper number of significant digits based on whatever tool we have that has 4 significant digits is to put this into scientific notation. So what we're going to do is put 5.060. And that has 4 significant digits, a captive 0, which is significant, and a trailing 0 with a decimal place, which is significant. Now you may have noticed that that is not, does not express the magnitude 50,000. So to express the magnitude of the number, we're going to put in our exponent. So we moved our decimal place from behind that last 0, 1, 2, 3, 4 places. So we're going to put that exponent times 10 to the 4 to give that number magnitude. To round 50,600 to 5 significant digits, keep the 5, 2, 3, 4, 5, 50600. Right now that has 3 significant digits. Plunk a decimal on there, and now we have trailing zeros and a decimal, which are significant. To 6 significant digits, 1, 2, 3, 4, 5, that 0 becomes a 1 because of the 6 directly to the right of it. So we have 50,600.1 milliliters. I'm getting sloppy. Don't let me do that. To 7 significant digits, now we're going to include the 6, which will also round up because of the 7 directly to the right of it. So 50,600.07 milliliters. And then to 8 significant digits, right? 1, 2, 3, 4, 5, 6, 7, 8. We stop at the 7, which rounds to an 8 because of the 5 directly to the right of it. So 50,600.068 milliliters. Please remember that when you are rounding a number from your calculator to the proper number of significant digits, you must express the magnitude of the number. Okay, I'll do the calculations in a separate video.